So finally, we're going to use random forest and gradient boosting to calculate the amount of damage that a insurance company is going to expect to pay for a person's claim. This is called a regression tree. Now, we've done this before, but now we're going to use random forest and gradient boosting. So again, we're going to load in random forest and GBM. So those guys are going to be loaded in. And as before, GBM is a very good algorithm for gradient boosting. However, XGBoost is considered to be the better one. And as you get more skilled with gradient boosting and R programming, you may want to switch over. But then again, this is a perfectly fine algorithm and certainly not a bad one to use. So let's load these guys in. And again, we're going to do a 70-30 split here. And you can see here that we've loaded in, we've got a train data set and a test data set. The average damages overall is 1,500. For our training, it's 1,512, and for our test, it's 1,507. So those are all very close. We'll start by building a decision tree. And we're going to want to set this. There's a couple of different options when you have a regression tree. I found that with this particular data set, Poisson was giving me a good result, but you're going to want to try other splitting metrics, not just Poisson. I think they have ANOVA and a few other ones. Try many things and see which one works, but we're just going to stick with Poisson because I happen to know that it works well. And there we go. And we're going to want to print the tree. And I've actually included a few extra arguments to the R plot here to make my decision tree look a little bit more appealing. So that looks, I think, a lot more readable. I'll show you what the other one looks like. Let's just for fun. If I was just going to take the defaults, so if you don't use any of these arguments here and just go this way, your tree will look like this. And it's got, you know, this exponential notation, and it has the number of records in the node. I find that difficult to read, so I'm going to go with this right here, and I think it will be a more readable tree. But that's up to you. So I think that this is just telling me the amount, 1,513, and 100% of the people are here. Over here, the damage is $409, and that's 20% of the people. So that's, you know, what this is telling me. But this is, again, a simple vanilla decision tree. And let us now see if we can get the model importance of the variables, because trees will give us the importance. And there they are. We can look at those later, but let's also predict our test data set. Here's our tree model and our test data set, and we're going to put the results into PT there. So the variable PT. And we've also computed the root mean squared error of the tree. So that's going to be the square root of the mean. We take the target variable minus my prediction. We're going to square that, calculate the mean, and then do the square root. So that's the root mean squared error. I like that metric. There's other ones, and they will all tend to agree as to what the best model is, but not all the time. But that's the metric I personally like. Now let's build a random forest. And again, we set the importance to true so that the random forest will tell us what variables are important. So this might take a few minutes. So again, I'm going to put this on pause, and I'll wake up when it's completed running. And we are back, and it took a couple of minutes again. And let's take a look at the variable importance and the variable importance plot. So again, the blue, when you look at the damages that you have to pay to fix a car, Blue Book value seems to be important, makes sense. Again, urban, home value, these are the values that seem to predict that. Let's move on to, we're going to predict the damages. So here's our RF model and our data set. We're going to put the results into PR here, and then we're going to calculate the root mean squared error of the regression. Excuse me, the random forest. And there we go. And last but certainly not least, we're going to use the gradient boosting. Now, for the flag, the 1 and 0, we were using a Bernoulli distribution. I find that Poisson seems to work best for a regression tree. These are things that you just have to do a little trial and error, but let's do that. And this should be almost instantaneous. This is quite fast. And the gradient boosting tree is training, and it's done. And again, you can see here that the tree variable importance plot for gradient boosting for GBM is not all that useful, but you can look up here at the variables, and this will give you a much better idea of the variable importance. Finally, we're going to print for our test data set. We're going to calculate the root mean squared error for the tree, the regression, the random forest, and the gradient boosting. The lower the number, the better. So let's see which one performed the best. And there we go. So the tree gives us an average root mean squared error of 4689. The random forest 4648, that's better, and 4631 for the gradient boosting. So again, for this data set, the gradient boosting appears to be outperforming everyone. Again, not to sound like to be repetitive here, but you must not assume that gradient boosting is always the best. It is a very good and oftentimes is the best, but random forest sometimes will be the best. Occasionally a simple tree will be the best. Try them all. And then when you start getting into other modeling types like regression or neural networks, again, there's never going to be one type that always wins. You have to try many types. But anyway, this is the gradient boosting and random forests.